Hi everyone, welcome to the ICTS String seminar. So today we have Madhu Mishra from IISER Trivandrum who will be talking to us about higher derivative actions in supergravity. So over to you, Madhu.
So good afternoon, everyone. I would like to thank the organizers for the invitation. I am genuinely grateful for having this opportunity to present my work here. I will be talking about the construction of higher derivative action n is equal to 2 supergravity in 4 dimensions. I want to preface this talk by saying that instead of just sharing the punchline, I will also be highlighting the computational techniques employed in general for the construction of such supersymmetric invariants. And I will illustrate these techniques with the help of a simple example. But first, why do we even want to construct such actions? What is the motivation behind it? So one of the primary motivation for us is black holes because of its key property that they have entropy. In 60s and 70s, Bekenstein and Hawking wrote down this pioneering formula for the entropy of black hole in a semi-classical picture, where the entropy is given as kb times area of horizon by 4 in Planck units. This formula is beautiful because it has all the universal constant and it relates thermodynamic quantity to a geometrical quantity. It also encapsulates a profound idea that just like air around us, black hole too is made up of a set of microscopic systems, which raises the natural question about the statistical origin of black hole entropy. So the question is, can we write black hole entropy in terms of its microstates? If yes, what are these microstates? And to answer these questions, we need a quantum theory of gravity. Enters string theory. Out of its many triumphs, string theory is the only theory that provides microscopic description of black hole. And the first statistical entropy was calculated in string theory in 1996 by Strominger and Baffa by realizing black hole as a brane system. Their result agreed with Bekenstein and Hawking area law and also provided subleading corrections to the entropy. These subleading corrections in a semi-classical theory correspond to a finite sized black hole and arises from the high derivative terms in the action. So note, although this leading term in the entropy is universal, the coefficient appearing alpha and beta here will depend on the nature of the theory. So despite the theoretical success of string theory, at present, it cannot be experimentally tested due to the lack of accelerator with sufficiently high energy. Thus, we rely on the theoretical test to verify the mathematical consistency of string theory. And supergravity theory, being the low energy limit of string theory, can provide us with such consistency checks. One of such tests is the matching of microscopic entropy computed in string theory with the macroscopic quantities entropy computed in effective supergravity description. Therefore, higher derivative terms in the supergravity action, since they provide subleading corrections to the entropy, plays a crucial part in establishing such connections. All right, so here I will mention some of the known results in n is equal to 2 supergravity in 4 dimensions to further motivate our work. So 40 years back, supersymmetric pure Weyl tensor square action was obtained by these authors, which in 2006, these authors used to calculate the entropy of BPS and non-BPS black holes, in which they found that for BPS black holes, the microscopic and the macroscopic entropy shows a perfect agreement. However, for non-BPS black holes, they showed that there is a disagreement, which led to a puzzle for entropy. And it also indicated that the supersymmetric curvature square term is not complete. And by not complete, I mean that the 4D Weyl tensor square action does not contain all the terms which would come from the dimensional reduction of a 5D curvature square action. And almost 7 years in 2013, almost 7 years after this puzzle, a new supersymmetric higher derivative invariant was obtained as a combination of Ricci tensor square and a Ricci scalar square. which resolved this non-VPS black hole entropy puzzle in 2016. Another important and related result is that there exist two types of Weyl multiplet in 4 dimensions: standard Weyl multiplet and recently constructed dilaton Weyl multiplet. And we will study about these Weyl multiplet in the later part of this talk. But I just want to highlight that here, all the results that I have mentioned so far have used standard Weyl multiplet for their construction. And we, however, like to explore dilaton Weyl multiplet to construct such supersymmetric invariants. Then, are there any questions till this point? Okay, if not, so now that we are motivated enough to construct higher derivative action in supergravity, we want to learn the techniques to do so. And before we move to the construction of these actions, I want to point out that it is advantageous to construct off-shell actions where the SUSY algebra closes without having to impose equation of motion for technical reasons, but most importantly, off-shell actions are necessary to facilitate the computation of quantum entropy of a black hole. And for the construction of off-shell higher derivative action in supergravity, one uses superconformal tensor calculus. So the plan of talk is from here on is as follows. So first, we will learn the technique with the help of simple examples. So we will do a simple example to learn the superconformal tensor calculus. Then we will learn this technique with the help of simple example without including any supersymmetry. And once we are comfortable with the technique, we will see the construction of for SUSY case, where we will encounter Weyl multiplet. We will discuss the difference between two Weyl multiplet, and we see why we choose dilaton Weyl multiplet for our construction. Most importantly, we will see the map that exists between dilaton Weyl multiplet and Yang-Mills multiplet, which we will exploit for our construction of Riemann square invariant. All right. So to recap, superconformal tensor calculus is a method to construct a off-shell Poincare supergravity using superconformal symmetry. So the idea is that to construct a supergravity theory that first have larger group of symmetry, and hope that when we have larger group of symmetry, since symmetry is restrictive and constrained, it would be easier to construct an action. And to finally obtain a supergravity in Poincare theory, we will gauge fix those extra symmetries. This formalism is based on gauge equivalence principle. And this program has following steps. So first we will introduce extra symmetries. So for example, we have the larger group has this, and we want our final theory to be invariant under some group, say GP, where so GF is greater than GP. So first we will write the algebra for this larger group of symmetry, and then we go to the gauge theory and introduce gauge multiplet. We will write compensator to compensate for these extra symmetries. Hence, we will construct an invariant action, which will be invariant under this larger group of symmetries. Then we will gauge fix these extra symmetries and finally obtain an action which is invariant under the smaller group of symmetry that we wanted in our theory. Okay, so let's consider a simple example to understand this program. So our aim is to start with conformal group. We will show that conformal gravity is equivalent to Poincare gravity. Here we have conformal algebra, and the generators of conformal algebras are translation, Lorentz transformation, dilatation, and special conformal transformation. And these are the corresponding parameters. And here I have listed out the non-vanishing commutators for this conformal algebra. Now we want to construct conformal gauge theory, and we know from gauge principle that once we make the symmetries local by making symmetry parameters space-time dependent, we have to introduce gauge fields. So these are the corresponding gauge fields for local symmetries. And the transformation of any generic gauge field under local symmetry is given as this. So here I want to write down, so for example, if I want to write down the transformation of E mu A under local translation, then this index A will correspond to the symmetry associated with gauge field. This, one second. So this capital A correspond to the symmetry associated with gauge field, and this epsilon will correspond to the parameter associated with the transformation symmetry. So if I want to find transformation of E mu A under local translation, what I will have here is this. So xi is the parameter corresponding to local translation. And since this is the parameter corresponding to the symmetry group here, it's the same as E mu A. So I will write this thing here. And now I have to find what is H mu B such that under commutation relation, I should get translation. So just by looking at this algebra, you can see what are the commutation or what are the symmetries that will give me E mu as a final product. So these are the two commutators that will contribute here. So the H mu B can be either B mu and it will be E mu AB also. So by finding the structure constant by looking at the algebra, we can finally write down the transformation of E mu A under local translation as this. So this is the transformation of E mu A under local translation. Similarly, if I want to write the transformation of E mu A under other fields, for example, all these symmetries, symmetries other than local translation combined called as standard gauge transformation. And here I will denote it with STD. Now, if you look at this term, this A corresponds to the index of gauge field, and since we are only taking transformation under standard gauge transformation, this term will not contribute. This term will not contribute here, and we will only have epsilon C H mu B. So we want to see any two commutation relation which gives us translation as a final product. So here again, the only thing which will give us translation in the product is omega mu AB and dilatation. So we can write the standard gauge transformation as this. Is it clear?
Yes,
Okay.
yes, it's clear.
Okay, fine. So if it's clear, then now we have the standard gauge transformation of E mu A and local translation of E mu A. So I will just write it finally here because this will be used later on to explain some important result. So this is the standard, and we can also find the field strength corresponding to any gauge field. For example, R mu A. So if I want to write the field strength corresponding to translation, it will be, so you can check that it will be this. Which we can see just from here, that what we have to do is just replace the parameter with the gauge field and anti-symmetrize. And that's how we will get the curvature.
Can I just ask one question?
Yes.
This part of the analysis is, I mean, just like how you would proceed for non-abelian gauge theories. Is that right? Except
Yes.
that the gauge group is non-compact.
Yes, sure. Yeah.
Okay,
exactly.
so nothing. Yeah. So far there is no extra subtlety that has come in because of supergravity or anything.
No,
right?
no.
Okay.
I'm just for here. I'm just considering conformal group. So there is no supersymmetry.
Okay. Okay.
Okay. So now that we have this thing, we want to construct. We constructed conformal gauge theory, we want to go and construct conformal gravity theory. So in gravity theory, what we have is that the spin, omega mu AB will be dependent on E mu A. However, in conformal gauge theory, these two fields are independent. Also, the other subtlety is that all the gauge symmetries in conformal gauge theory acts on internal space. However, in gravity theory, local translation should act on space-time, such that we have a general coordinate transformation. So we want to overcome these shortcomings, and that will be done by imposing some constraint on curvatures. And how we are going to do that is as follows. So what we want to do is we want to identify local translation with some general coordinate transformation. Here I will introduce covariant general coordinate transformation, and because the general coordinate transformation will act on any field, for example in E mu A as Lie derivative, and it is not covariant with respect to other gauge symmetries, for example dilatation and special conformal translation. And to make it covariant under all the other gauge symmetries, we will introduce a transformation which is called covariant general coordinate transformation, and it is defined as just by subtracting this gauge dependent transformation. Just like we did for covariant derivative, when we went from partial to covariant derivative, what we did is we subtracted a gauge dependent quantity. So that is how we are going to change this general coordinate transformation to covariant general coordinate transformation by just subtracting this gauge dependent quantity. So here I correspond to standard gauge transformation. So all the transformation except the local translation. And if you see that when we calculate this covariant general coordinate transformation for E mu A, basically what we have is this. This is the Lie mu A plus from this part, this is the general coordinate transformation, and what I'm going to do is subtract this thing. So we saw that this is the standard gauge transformation of E mu A, and what we want to do is just replace this parameter with this quantity, the scalar product of xi, which is the parameter of local translation, and the gauge field of corresponding to this parameter, which is this AB. Similarly, here we will replace with xi c and b mu, which is the gauge field corresponding to this parameter. So in final, we will have this quantity. Is this clear till this point? How I got this
You're just taking a particular combination of all the symmetries that you have found, and you're calling it covariant general coordinate transformation. Is that
so?
Right?
We have basically we have this general coordinate transformation, which is like a Lie derivative. So it's not just local translation, but plus it is general coordinate transformation which will act on space-time. And to make it covariant, what I'm doing is I'm taking this standard transformation and replacing the parameter with this thing, scalar product of xi with the gauge field corresponding to the parameter.
But is this transformation a special case of what you wrote down earlier, the gauge transformation that you wrote down in the previous slide?
No, not the special case. What do you mean by special case?
That you restrict the transformation parameters to certain form, and then you get this covariant general coordinate transformation? I'm just trying to say, how do you know that this is a symmetry? This covariant general coordinate transformation that you defined.
Yes.
How do you know that this is the symmetry of the theory?
Yeah, so because
if it's a combination of known symmetries, then of course it will remain a symmetry.
yeah, so it is combination of known symmetry. So this term has all the symmetries that we had already. So this I correspond to standard gauge symmetries, which is basically dilatation and special conformal transformation and Lorentz transformation. So all include the symmetries that I already had in the algebra or in the theory.
Okay.
So this will remain the symmetry of the theory.
Okay. So in that sense, it's a special case because you're just setting the symmetry transformation parameters to some specific values, right?
Yes.
That's what you are saying.
That's correct.
Okay. Okay. Thank you.
I have a related question.
Yes.
Hello. Can you hear me?
Yeah, I can hear you, sir.
Yeah. So the question is, I mean, would you say that gravity is not a local theory, a global theory?
No, gravity is a local theory. The difference
So
between gravity.
So what do you mean by general? I mean, what do you mean by CGCT? What are the CGCTs, delta CGCTs? Covariant general transformation. So when you are covariantizing a general coordinate transformation, what do you exactly mean by that? Because they are already covariant, right, in a certain sense, because the theory is local.
Yes.
Gravity
So what I mean by
isomorphism symmetries are local symmetries, right?
Yeah, they are local symmetries, and by covariant general coordinate transformation, what I mean is that gravity in this setup we have conformal symmetries as well. It's not just Poincare symmetries. So to capture this other symmetries also, we have to include this term. So that is why this covariant general coordinate transformation is coming. So if we only had Poincare symmetry, then the general coordinate transformation will suffice. Because we have conformal gravity, the other symmetries will come into the picture, and that is why we have to define a quantity called covariant general coordinate transformation.
Yeah, but in order to incorporate the conformal symmetries, you are again incorporating the Poincare and the translation symmetry, the Poincare symmetries.
Yes.
You're just gauging by the Poincare symmetry. So in what sense is it conformalizing it?
So initially, if you have a gauge theory, all these local symmetries, they are acting on tangent space, but not on the space-time. So this identification, however, the general coordinate transformation acts on space-time. So that is why we have to come from local translation to general coordinate transformation. This part you understood. And then to encapsulate conformal symmetries, we have to covariantize this general coordinate transformation. So in final, we will have conformal gravity, but not the conformal gauge theory. So basically to confirm conformal gauge
Okay,
theory.
so you're saying that the extra symmetries act on the A index instead of the mu index.
Yes.
Maybe you can postpone the discussion to the last or something.
Yeah, sure.
You can go on.
So A is the tangent space index. This is the space-time index.
Yeah, I got it.
Yeah. Okay, so yeah, so we wrote this conformal, so covariant general coordinate transformation for E mu A in this form, and we can show that this can be written as this thing. Local translation minus some covariant quantity, which is the curvature of this translation, which we calculated in the previous slide. So we can just show that this quantity, this whole expression is nothing but can be divided into these two forms. So if we want a conformal gauge theory to be gravity theory, we have to impose this equal to 0, because we want to identify local translation with covariant general coordinate transformation. So till this point, the theory was gauge theory. It was the local translation was acting on tangent space. Now that we have imposed this constraint, and we have identified local translation with covariant general coordinate transformation, we can say that we have a theory of conformal gravity. Not just that, we also want to lessen the degrees of freedom in our theory, because we want the final aim is to go to Poincare gravity. So we want to lessen the degrees of freedom, and for that we will look at the structure of other curvatures in the theory, and we found that the curvature of Lorentz transformation is given as this, and it has F mu A, which is a gauge field corresponding to special conformal transformation. It appears algebraically here. So we can impose this kind of constraint to obtain F mu A as a dependent field. And if you count the degrees of freedom here, or not degrees of freedom, if you count the components of this constraint, it is actually equal to the components of F mu A. So after imposing this constraint, you can obtain F mu A as a dependent field, and you can show that this will be equal to Ricci tensor, quantity of Ricci tensor, and something proportional to Ricci scalar. Okay, so now that we have imposed these constraints and we have shown that F mu A and omega mu AB is dependent, which is the nature of a gravity theory, we will count the degrees of freedom. So when we count optional degrees of freedom, we subtract gauge symmetries from the number of components of independent gauge fields in the theory. So if you look at conformal gravity, we have two independent gauge fields. So the number of components is this, which is 20. And the gauge symmetries we have are translation, which has 4, plus Lorentz transformation, plus dilatation, and also special conformal transformation. So we have 15 symmetries. So after subtracting the number of component of independent fields with the gauge symmetries, we have 5 optional degrees of freedom in conformal gravity. And we know in Poincare gravity, we only have E mu A as an independent field, and we have translation and Lorentz transformation. So we have 10 symmetries and 16 components, which means we have 6 optional degrees of freedom in Poincare supergravity. And if you want to go from conformal gravity to Poincare gravity, we need 1 degree of freedom to compensate for this extra symmetry. And we will introduce this scalar field as a compensating field. Okay. So this is the action that we have introduced, which is coupled to conformal gravity. And this action has Weyl weight 1, and it doesn't transform under Lorentz transformation or special conformal transformation. So this is the transformation of scalar field, and the covariant derivative, hence we can write as del mu phi minus b mu phi. And since b mu transform under special conformal transformation and Lorentz transformation, the de-L'Alembert of the scalar will have these gauge fields here. And after imposing this gauge fixing condition, b mu is equal to 0, we can obtain that the action is this. where F mu A also we have obtained. We have showed that F mu A is proportional to a Ritchie's tensor and a Ritchie's scalar term. And after imposing this after writing this dependent field and also imposing the constraint on B mu gauge fixing condition is equal to B mu is equal to 0, since B mu transform under this special conformal transformation, setting B mu is equal to 0 will break the special conformal symmetry. And hence we have this action which has Poincare, which has local translation symmetry, Lorentz transformation, as well as dilatation. Now to break the dilatation, we will fix the scalar field to some constant. And once we do that, we will obtain this Einstein-Hilbert action. So what we have shown as here is that conformal gravity we have shown that the conformal gravity is gauge equivalent to Poincare gravity. In a schematic way, this is what we have shown. So we started with Weyl multiplet, which has E mu A and B mu as independent fields. We added a matter field as a compensator, and finally we gauge fixed dilatation and special conformal transformation and obtain a Poincare gravity. Is this part clear? Because now we are going to move to supersymmetric construction. Okay, so now we move to supersymmetric theory. So this is the superconformal algebra. This is the superconformal algebra, and we have generators of superconformal group, these 4 generators. And we also have Q supersymmetry. And since it's a conformal group, we also have special SUSY here. So for example, this is the conformal part of SUSY. So if Q supersymmetry closes to local translation, the Q special supersymmetry will close to special conformal translation. And to close this algebra, we will also need R symmetries. So this is SU2 in n is equal to 2, and this is U1. And this is the superconformal algebra. So after we have superconformal algebra, what we want is to construct a multiplet over which this superconformal algebra acts. In other words, we want to find the realization of this algebra in terms of fields. So once we have the multiplet, we can construct action. So these are the gauge fields corresponding to all these symmetries. Now again, we will do the same thing. We will, to go from conformal gauge theory to conformal gravity theory, we will impose constraint on the curvature of local translation, and to lessen the degrees of freedom, because we can obtain F mu A algebraically from this constraint, we will impose this constraint. And also, if you look at the curvature of Q SUSY, we can see that it is proportional to a term like this, which means this S SUSY, the phi, is the gauge field corresponding to special SUSY. So this appears algebraically in this curvature. So after imposing this constraint, we can also obtain phi mu I as a dependent field. And once we calculate the degrees of freedom, we will see, this is the counting of the offshell degrees of freedom for all the fields. We will see that the degrees of freedom, bosonic and fermionic degrees of freedom, will not match. Hence, we have to add some new fields such that they form a super multiplet. So for a supergravity theory, we should have an equal number of bosonic and fermionic degrees of freedoms. And to match the bosonic and fermionic degrees of freedom, we need to add extra set of auxiliary fields and to the multiplet, as well as we have to modify the superconformal algebra to soft superconformal algebra, where the structure constants become the structure functions depending on the auxiliary fields. The multiplet that contains gauge field are called Weyl multiplet in superconformal theory, and there are a couple of ways to select auxiliary fields which lead to either standard Weyl multiplet or dilaton Weyl multiplet. So if we choose these set of auxiliary fields, the Weyl multiplet is called standard Weyl multiplet. However, if we go for this set of auxiliary fields, this multiplet is called dilaton Weyl multiplet because it has a dilaton field. And we want to use dilaton Weyl multiplet for our construction. And why dilaton Weyl multiplet? Because if you work with dilaton Weyl multiplet, we only need one compensating multiplet to go from conformal theory to Poincare theory. However, in standard Weyl multiplet, because of presence of this field, this will appear in the action as a Lagrange multiplier, and to get rid of this field, we'll have to use another compensating multiplet. So in standard Weyl multiplet, if you start with superconformal theory, we will have to use two compensating multiplet to go from conformal to Poincare. However, in dilaton Weyl multiplet, only one compensating multiplet is required. Also, it has.
Well, are these two equivalent? These at the end, these two theories will be equivalent or not?
Yeah, so in 5 dimension, they have shown that these theories are equivalent. And in 4, we have not shown, but one can show that because all these fields are basically can be written in terms. So there is a relation between dilaton Weyl multiplet and standard Weyl multiplet. So in dilaton Weyl multiplet, all these TAB, D, and chi will appear as a composite field. So we can go from one theory to another theory. So in my understanding, they should be equivalent.
Can I make a comment?
Yes.
Yeah. So actually, you can obtain a dilaton Weyl multiplet from standard Weyl multiplet. There is a relation which can express the a standard Weyl multiplet from the dilaton Weyl multiplet. You can express the fields, auxiliary fields of the standard Weyl, the auxiliary fields of the dilaton Weyl multiplet in terms of the auxiliary fields of the standard Weyl multiplet. But the inverse relation is not true. So basically, because some of these fields in the standard Weyl multiplet are all these fields in the standard Weyl multiplet are actually auxiliary fields, but which means they don't have any degree of freedom. But that's not true for the fields in the dilaton Weyl multiplet. So this W mu, for example, would correspond to a graviphoton, and W tilde mu would be the dual of that graviphoton. Whereas in the standard Weyl multiplet, all these fields are auxiliary fields. So it's possible to go from one to another. Like if you have a theory in terms of standard Weyl multiplet, you can write down a theory in terms of dilaton Weyl multiplet. But if you have a theory in terms of dilaton Weyl multiplet, it's not necessary that you can write down a theory in terms of the standard Weyl multiplet. So it's not equivalent because the relation is one way. It's not 2 ways.
So if we look at the particle spectrum in these two theories, they are the same or they are not the same?
Yeah, so basically, dilaton Weyl multiplet is basically standard Weyl multiplet plus vector multiplet in a crude way. So
it already has one extra vector multiplet.
Exactly. So this is, in standard Weyl multiplet, you need 2 compensators, but one of the compensator is already included in the dilaton Weyl multiplet.
I see. Okay, thank you.
So is the understanding that is obtained after some sort of gauge fixing or something like previous case?
No.
After coupling the on-shell vector multiplet to the standard Weyl multiplet, we obtain the dilaton Weyl multiplet.
So you have to use the equations of motion of the vector multiplet to there is a procedure to do that. So, but that's what I said in the crude sense, the dilaton Weyl multiplet is standard Weyl multiplet plus vector multiplet and eliminating some degrees of freedom of the
Yeah,
vector using the
eliminating by gauge fixing or some other
equations of motion.
equation. Okay.
So,
But equations of motion means the dilaton Weyl multiplet then has additional plane wave solutions or not compared to standard Weyl multiplet? If we just think of the quadratic part of the two actions, then will the dilaton Weyl multiplet have some additional plane wave?
I mean,
That is extra vector multiplet that you said,
exactly.
that will have some vector fields, right?
So there are propagating extra propagating modes.
Yeah, that's what I meant. So those vector fields will be extra propagating modes, which will not be there in the standard Weyl multiplet.
Right. Yes.
I see. Okay. Okay. Thank you. So if you have a theory then without any extra vector multiplet, then you cannot use the dilaton Weyl multiplet. Is that right?
No, I mean, you can couple it to additional vector multiplet. So when you write down a theory with standard Weyl multiplet, you need one vector multiplet to go to Poincare supergravity. But other than that, you can couple it to additional vector multiplets. With
Yeah, you can. But suppose your theory doesn't have any additional vector multiplet.
Yeah, then you just work with the dilaton Weyl multiplet, you will get a pure Poincare supergravity.
I see. Okay. Okay. Thank you. So standard Weyl multiplet by itself is not good enough for Poincare supergravity, you are saying.
Right.
That you need a vector field anyway.
You need one vector multiplet.
Okay. Thank you.
So as Bindu sir pointed out that because we get dilaton Weyl multiplet from standard Weyl multiplet, if you look at these fields, these omega mu x and these fields are part of vector multiplet, and which will appear as a auxiliary field or meta field in dilaton Weyl multiplet. They are not they have a dynamic degrees of freedom in dilaton Weyl multiplet. However, in standard Weyl multiplet, these fields were auxiliary. And one other special thing is that in dilaton Weyl multiplet, we have a two-form field inbuilt, which a higher derivative action that would like to construct from compactification of string theory needs to have a two-form field. And in standard Weyl multiplet, there is no such field, and it should come from some other multiplet. So that is another advantage of using dilaton Weyl multiplet. And the advantage that we used was the map between dilaton Weyl multiplet and Yang-Mills multiplet. So there exists a map between the curvatures of dilaton Weyl multiplet and Yang-Mills multiplet, which we can use to construct a high derivative action just by writing the action for Yang-Mills multiplet. And this is what we are going to do now. So these are the list of some off-shell compensating multiplet in 4 dimensions for n is equal to 2 theory. Although I won't be using all of it, what I will be using is chiral multiplet and Yang-Mills multiplet. And we will see that we can embed one Yang-Mills multiplet into chiral multiplet, because to construct an action, we want to use chiral density formula, which is constructed out of chiral multiplet. So in chiral multiplet, we have a complex scalar, we have a complex SU2 triplet, we have anti-self-dual Lorentz tensor, and we have another complex scalar. They differ in their Weyl weight. So this has Weyl weight 2, and this will have Weyl weight 4. Similarly, we have 2 fermion SU2 spinner, and they both have Weyl weight. This has Weyl weight 5/2, and this has Weyl weight 7/2. And in Yang-Mills multiplet, so this is the vector multiplet that people are familiar with. And the Yang-Mills multiplet is just the same as vector multiplet, but the additional gauge group, which we denote by alpha. And alpha takes value from 1 to n. That is why we have 8n plus 8n off-shell degrees of freedom. So this is also complex with Weyl weight 1. And chiral weight -1. This has chiral weight -2. Okay, so this is the density formula that is known in n is equal to 2 in 4 dimensions. And to construct a high derivative action, if you only want bosonic part, what we want to know is what is C in terms of other multiplet. So if we want to construct if we want to construct a action for Yang-Mills multiplet, we want to use this chiral density formula and embed the Yang-Mills multiplet in terms of chiral multiplet. So what we need to do is find a composite constructed out of Yang-Mills fields, which has all the required property of the lowest component of chiral multiplet. So basically, this is what we have done here. So this is the lowest component of chiral multiplet. It has Weyl weight 2 and chiral weight -2, and we have constructed a composite out of Yang-Mills multiplet. So these A alpha and A beta are components of Yang-Mills multiplet. This has Weyl weight 1. So together they have Weyl weight 2 and chiral weight -2. And what we will do is we will find all the components of chiral multiplet in terms of Yang-Mills multiplet. Basically, what we want to do is we want to find this component C, which has the highest Weyl weight, which is 4, in terms of Yang-Mills components. So to do so, what we will do is we will just do the successive application of supersymmetry in these expressions and find these fields. So I can show how one does that. Just okay. So for example, we start with this. This is the chiral multiplet. These are the components of Yang-Mills field. And the transformation of chiral multiplet is this. Now we already know what is this component in terms of Yang-Mills multiplet. We want to find out what is this component in terms of Yang-Mills fields. So we will do this transformation. This alpha beta is symmetric under alpha and exchange of alpha and beta. So this will be just 2. And we also know the transformation of Yang-Mills fields, which is this. So it is just I alpha, A beta, A alpha beta. And by looking at this equation and this equation, we can identify this chiral component of chiral multiplet as this combination of Yang-Mills fields of Yang-Mills multiplet.
Is A alpha beta symmetric?
Yes, yes, it is symmetric because this is basically trace.
Oh,
So this is trace. So on inside trace, alpha beta is symmetric.
yeah, because otherwise the first expression won't work. Anyway, okay, go ahead.
Yeah, it's symmetric under A alpha and beta. That is why this is 2, and that is why we can write this expression. So what we obtain is other second field of chiral multiplet in terms of this combination of Yang-Mills multiplet. Similarly, by successive doing this thing, we can also obtain Bij and FAB minus, and after doing further supersymmetric transformation, we can obtain C. Once we have the C, we can write it in the chiral density formula, and what we will get is this. So this is the action for Yang-Mills multiplet in superconformal theory. So we still have all the conformal symmetries, and we have supersymmetry. So we have not gauge fixed yet. So what we will get is the Yang-Mills action in superconformal theory. Here I have highlighted some fields in red. So these fields are basically dependent fields. And when we go after gauge fixing, when we go to Poincare theory, these are the fields given in terms of curvature square or curvature terms. So this is the field strength corresponding to two-form gauge field that we had in dilaton Weyl multiplet. These are the field strength corresponding to gauge field in Dilaton Weyl multiplet. This is from, again, gauge field from the Dilaton Weyl multiplet, and this is the Ritchie scalar. And once we substitute this back, we will get Yang-Mills action in super Poincare background. So I have gauge fix. I have not given the gauge fixing condition here, but if once you gauge fix using the gauge fixing condition, which we saw for conformal theory, similarly we will use here also. We can use b mu is equal to 0 to gauge fix special conformal transformation. We can use x is equal to x bar. So x is the complex scalar in the Dilaton Weyl multiplet to gauge fix u1. We can fix this to some constant to gauge fix dilatation, and we can use this symmetry to gauge fix S sub C. So in the end, we will have Poincare symmetry and SU2 symmetry. We have not yet fixed SU2 symmetry. So you can see from here only that we don't, just by Dilaton Weyl multiplet, we can gauge fix all the external symmetry except for SU2. So to fix SU2, we will need linear multiplet, and that's all. We just need one compensator to go from conformal supergravity to pure Poincare supergravity. And this is the
So
action.
indeed, you're gauge fixing, right? I mean,
Yes,
the point that I was raising before, you're indeed gauge fixing in some sense. I mean, in order to go from the Dilaton Weyl multiplet to the lower multiplet, you're gauge fixing, right?
Which lower multiplet?
I mean, this b mu equal to 0, x equal to x
Yeah.
bar.
Yeah, these are the gauge fixing conditions that I have listed.
Yeah.
What I was saying that I have not listed here the gauge fixing condition, but these are the gauge fixing condition I used to go from this action, the action 14 to action 16.
And the action 16 is not the standard Weyl multiplet, no, something else.
No, there is no standard Weyl multiplet. We are only dealing with Dilaton Weyl multiplet, and the action is this action is for Yang-Mills multiplet in the background of Dilaton Weyl multiplet.
Okay. And another question is, where are the fermionic fields for
So
the supersymmetric?
I am just writing bosonic here because it will be cluttered otherwise. So for here I've just mentioned the bosonic action, but you will have fermionic parts also. I have not mentioned here, but you will get it from there, because once you'll do this supersymmetric transformation, the C will have all the fermions and boson both. So I've just I'm just concentrating on bosonic part here. Yeah.
Oh.
Okay, so this is the Yang-Mills action in Poincare supergravity with SU2 symmetry. So I have not gauge fixed SU2 symmetry. Yes, we will keep it and we will fix it in the final action when we have Riemann square action. So now we are going to use this map. So I'm not going to show how we obtained this map because it's very tedious process that we did to find this map. What I'm going to do is I'm going to list down the transformation of those curvature and show you how they look identical under some identification. So these are the curvature. So this KAB is basically the combination of this FAB and GAB, which I already told you that it's a field strength corresponding to omega mu and W mu and W mu tilde. This is the spin connection, and this is the field strength corresponding to B mu nu. So basically this, if you see, this appear as a some sort of torsion here, and then this is the transformation of this curvature. This is basically the curvature of Q sub C in Poincare supergravity. So instead of writing RQ mu nu, I am writing, which I wrote it in Superconformal. In Super Poincare, I am denoting this curvature as this thing. So this is the Q sub C curvature only, but in Poincare theory. And this omega minus mu AB is this combination. VABIJ is the curvature associated with SU2 symmetry. Okay, and these are the Yang-Mills. This is the transformation of Yang-Mills field in Poincare supergravity. So I have used gauge condition to change the transformation of Yang-Mills field. So these transformations are in super Poincare theory. So if you look at these two transformations are exactly identical under this identification. So if you change A alpha to this, lambda I alpha to this psi ABJ, and C mu alpha with minus omega mu minus. So it's not just omega mu AB, but one with the torsion. And this Yij of Yang-Mills multiplet is identified with curvature of SU2. Then these two multiplets are identical and their transformations are identical. Hence, we can use this map and put it in the Yang-Mills action that we obtained and get this action. So in that action, we had field like this, right? Which was basically B mu nu. And here we know that C mu is identified with spin connection with torsion. And once you put it in this action, what you get is Riemann tensor square action. So it's not exactly Riemann square because you have omega minus, but we have a relation between Riemann tensor and this quantity in this way. So if you want a pure Riemann square action, you can use this relation and put it in the action, and what you get is a Riemann square action. Yes. So is there any question till this point? Okay, if not, so just to recap,
So in the component notation, this will be identical to what you get from the standard Weyl multiplet?
No, actually not. So because there are few terms which are not there in standard Weyl multiplet, which we will have here. So this H here, this field strength is depends on omega mu bare gauge fields of dilaton Weyl multiplet in this way. So for example, if I write omega mu nu rho, then you have terms like this. And if you put it back in this action, you have terms like Chern-Simon terms in the action, which is not there in standard, the action that is obtained from standard Weyl multiplet.
So can I make another comment here? I mean, here also in the dilaton Weyl multiplet, if you see there, the graviphoton gauge field and its dual gauge fields are there in the same multiplet. So the electromagnetic duality symmetry is like an off-shell symmetry in this action. Whereas if you use the standard Weyl multiplet, the dual gauge field doesn't appear directly in the action. So the electromagnetic duality symmetry there is an on-shell symmetry. It's a symmetry of the equation of motion. So in that sense, they are different.
They are different, yes.
I see. But suppose, I mean, you try to ask on-cell questions like correction to black hole entropy. Would you get the same answer whether you use this one or the other one?
Possibly. We have not yet investigated that.
That is our future work. We want to see that if this action will give the same entropy, and we want to see, so basically that will be the future direction that I will mention. But yeah, so okay, so now that we have constructed this Riemann square action in pure supergravity, I'm not going to list down all the calculation, but I'm just going to mention the results now. So this work was done with Bindusar in this publication, and we obtained the supersymmetrization of Riemann square action using this Weyl multiplet. We also did the supersymmetrization of arbitrary curvature square terms. So we obtained Weyl square term. We also obtained Ricci's scalar square action, and everything was encoded in this holomorphic prepotential. And we also coupled it with arbitrary number of vector multiplet using this pre-potential. And finally, the action, we can write it in a simpler form. We can write it in this way. So therefore, we get a series of interaction terms which are quadratic in curvature with field-dependent coupling. And if we just want pure curvature term, we will just fix g, the small g to 1, and we will get this sort of actions. However, in the action that we obtained in the paper has all sorts of terms, Chern-Simons terms, and the action that we have is till g is equal to 2. So we also have terms which is Weyl square multiplied with some auxiliary or field-dependent fields, and something like this also we have. So the action, this is the action that we obtained, and by arbitrarily tuning this alpha, beta, and gamma, you can get a required whatever action you want. You can choose it by just tuning this alpha, beta, and gamma. So the significance of our result is that we want to test the non-renormalization theorem, which that Ashok mentioned. We want to check that if this action will contribute to the entropy that has been calculated, and if they provide extra terms or they vanish if there is no other extra term. So we want to test that, which was done for this, the new higher derivative invariant, which was obtained that I mentioned earlier. It was tested for that they do not contribute to B-phase entropy, but they are only contributing to non-B-phase entropy. So that was the test that was done for that invariant, and we want to do the similar test for this invariant as well. And we also want to use dilaton-Weyl multiplet to investigate ADS for black holes and holographic principle in n is equal to 2 supergravity. Thank you. Yeah, I can take questions now.
If there are any questions.
So far that, I mean, you have not used it for any entropy calculation, you are saying?
No, not yet.
Okay. So you don't know if it gives the same answer or not in any example.
No.
I mean, I see. But if it doesn't give the same answer, then what would it mean? That there are two different ways of supersymmetrizing the Riemann square, or that any linear combination of this will also be supersymmetric?
I would say any linear combination of this should be supersymmetric.
Yeah, meaning suppose you take the earlier one, right, which people have used.
Yes.
And this one. And imagine that they give different answers.
Right.
Then could you just take any linear combination of these two, and that gives a continuous parameter family of possible supersymmetrization?
I don't know. Yeah.
But it would be very strange if it gives a different answer, right?
Definitely. Yeah.
Yeah. Okay.
In recent paper of Samir, they mentioned that we can use, so what they are showing is, they are showing that the higher derivative terms in 5D and the higher derivative terms in 4D are only differ by a total derivative. And they sort of mention that this action can solve their puzzle. They are not able to cancel some terms which should be cancelled, otherwise there is some mismatch in their calculation. And they mentioned that we can use dilaton-Weyl multiplet to kind of solve that puzzle that they are having. So yeah, we can do that. But yeah, I'm not sure how the entropy calculation will work out. We want to do that. Because of this Chern-Simons terms, the calculation is very non-trivial. Like there are too many interaction terms.
But the point is, if you look at an extremal black hole, then the geometry simplifies, right? I mean, then it basically all these things become numbers.
Yes, that's true.
Right, because of the ADS2 times S2. So it may not be very difficult to do the calculation.
Yes.
Right, for extremal ones.
For extremal, yeah. But
Yeah.
Yeah, like we were looking at your paper only to learn how to deal with Chern-Simons terms. We have started this calculation then, but then we diverted to something else. This is definitely is a future work that we want to look at.
Okay.
I mean, what we expect is that for arbitrary curvature square term, we should get the same entropy. I mean, that's the non-renormalization theorem that Madhu was talking about. Irrespective of what alpha, because I mean, in the earlier work, I mean, what we saw is that Weyl square, gives the correct entropy for the BPS black hole, but for the not for the non-BPS black hole. Whereas if you include the Gauss-Bonnet correction that Bernard, Kuzenko, and Ivanov and these people found, and then Navamita and their group showed that they can find the correct entropy for the non-BPS black hole as well, and it doesn't affect the entropy for the BPS black hole.
Okay, because that is the one which comes somehow from dimensional reduction of 5T. Is that right?
That is what exactly. So here we have like a arbitrary curvature. I mean, if you tune these parameters alpha, beta, and gamma, we have like arbitrary curvature square. So I mean, we would hope that it should not depend on this alpha, beta, and gamma, and it should give us the. I mean, that's what we hope, because.
I see.
Because that's what we also see right in 5D. I mean, whatever comes from the dimensional reduction of the 5D action, which has this gauge gravitational Chern-Simons term, those are the only terms that will matter for the entropy of the BPS and the non-BPS black holes. Any other term which is supersymmetric by itself will not affect the entropy. That's what we had argued earlier.
Yeah.
Right. So in that sense, we would expect that it should not depend on these parameters alpha, beta, and gamma. One has to show that explicitly.
I see. Okay. Okay. Thank you.
Thank you.
I have a naive question.
Yeah.
Hello.
Yes, sir.
Yeah. So, how would the transformations look if you formulated it in terms of the metric instead of the Weber? The general the covariant general coordinate transformations. How would they look?
Oh, the covariant general coordinate.
Because there is no A index, right? In the
Yeah, but we can relate Weyl and metric in term with respect, like using eta.
Covariant general coordinate transformation does not have any A index. That's just a definition that relates. I mean, CGCT and GCT, that relation does not have any A index. I mean, it doesn't matter whether you work it on Weyl or metric.
Everything is contracted and this.
no, what I'm asking is, since the CGCT, they depend on the A index. I mean, part of it is dependent on the mu index and part of it is dependent on the A index, right? Hello.
Yeah.
Yeah. Can you go to the CGCT expression? Yes, this one.
No,
But the definition here, it doesn't have any A index.
Yeah. So here, this extra term, this B mu A mu, okay, and the E mu omega mu omega mu AB U mu B, those terms act on the B index. I mean the extra space-time index, or rather the B index, right? Instead of the mu index, correct?
Yeah. So this CGCT here, she has calculated on E mu A, but you can, this formula number 6 is a general formula.
Yes.
If you want to calculate this on G,
Okay,
you can do that.
Okay.
You can do it for B mu as well.
G mu, B mu, whatever you want.
You can do it for B mu as well. So this A will not be there. So for B mu there is no A index. So this A is just the index for supersymmetry, for the symmetry, transformation symmetry. For example, if you have Lorentz transformation, this A will correspond to AB. But if you have dilatation, this A has no meaning. There is nothing. So just B mu is there. So A will correspond to the particular symmetry that you're taking. The gauge field, whatever gauge field you want, you can write this covariant general coordinate transformation for that. They do not depend on.
Okay.
Thank you.
Are there any more questions? If not, let us thank Madhu for the nice talk.
Thank you.
So see you for the next.
Thank you so much.